Right.
Just shoot me now.
All right, good.
When we don't have Bill Gates.
We'll have stuff that works all the time,
Yeah.
and logically. So, let's do this, and let's do this. We got the Excel for later. So, let's think back to yesterday, or Tuesday, I guess, Tuesday. What was the last thing we did? We did an activity for about an hour on Tuesday that involved dice. Perfect. The first thing I had you guys do was I gave you a bunch of dice, and I said, write down the average, the standard deviation, and the distribution of all possible outcomes of those dice. So the entire probability distribution for the dice. And the blue dice look like this. Yellow,
Yep.
green, orange, and red. And those are those beautiful distributions. And then I said, okay, that's great. And it is. It's great. Except for the problem, it's a little bit unrealistic. Because then I said the dice are going to represent your population, which they are. And what you just did here to get this population frequency distribution is a little bit fictitious. Can you ever do that with an entire population? Count the entire population and keep track of every single... No, there's no way you can do that. Your populations are usually far too large to actually do something like that. So then what did I have you do with the dice at that point?
You had us roll in groups.
Then I had you start rolling the dice in groups of 4, I believe, if I remember correctly. You start rolling your dice in groups of 4. I gave you the take-home quiz, and you guys were rolling the dice 4 at a time. And what did you do with those four sums? You averaged them. You averaged them. Say that again, Carrie.
And then you also got the averages from a couple other groups.
Good. So we ended up with, I think it was like 70, between 75 and maybe 50, depending on how many were in here. 50 or 75 or even 100 averages all together. And then you did what with those averages?
Histogram.
You made a histogram. Awesome, Stephen. And I had you put the histograms on the board. And although when you look at the original populations, they've got these goofy shapes. What was every shape of every sampling distribution that you put on the board?
Bell.
Every single one was bell shapes. The only one that was a little bit goofy was the yellow one. The yellow one was the highly skewed group, very highly skewed to the right, leaning left. There was still a little bit of a goofy tail on the right side of that one. But we'll talk more about that later. That tail will eventually disappear too, but not with your particular sample sizes of rolls 4. So what I want to talk about today is why that happened, and kind of go further into why that happened. Because here's the deal. You got these beautiful bell shapes, and those bell shapes have a high point, right? Each of those bell shapes had a high point. They had a max, if you will, or mode. Where was the high point or the mode of those bells located? Do you remember? Which center? I love it, Darla. Yes. Which center? Good, you're looking in the right place. It's up here. It's almost hidden by the camera's shadow, but the histograms were centered over which measure of center? The average, Victoria, yes. They were centered over the average. So wherever those bells were on the board, they were sitting on top of where the average for your particular distribution was. That was the beauty of it. So the blue distribution, the histogram was centered over 8.17. Yellow distribution over 4.5. Green distribution over 7. Now this, you might say, well, this is going to be, it's symmetric already. Well, absolutely. So it's already symmetric, so it doesn't have to go very far. But what's interesting is, we lost the tails and picked up more in the middle. Anybody remember why that is? Why did we lose the tail? Do you remember why? Yeah, absolutely, Jody, as we lose the tail, the middle has to rise to make up for that. Because what's the area under any curve? Always.
1.
Always 1 or 100% perfect. So if you're going to lose part of a curve, it has to go somewhere else to make up for it. Why do we lose the tails? Do you remember why they get lost? It's okay, you can say no at this point. Michael, go ahead.
The data follows the average.
Why?
Extreme
I'm going to keep asking why. Why do they go away? Why does that make them go away? You're so close. Nico. How come? Why do they clump to the middle and leave the ends?
I think it becomes exponentially harder and harder to get the...
That's why. Because it's hard to get the extreme. When you said extreme outliers, you got it. What is an extreme outlier? Something that hardly ever happens. So if you sample 4 times, if something hardly ever happens once, what's the chance it's going to happen 4 times in a row? it's exponentially to the fourth power less likely, if you will. That's why the tails disappear. The parts that are away from the averages fall off because they shouldn't happen. And if they shouldn't, the ones closer to, as Darla said, center, should, because there are more ways for that to happen closer to center. And then it fleshes out into a beautiful bell. The bell part, the clumping part makes perfect sense with Lori's exponential. The reason why it actually forms a perfect bell is actually much more convoluted. I put a justification on the enrichment page of the website if you want to check it out. It's got some calculus that you have to kind of slug through to get to it. Or you can just take my word for it and not worry about it. The bells show up. It's beautiful. And we're going to analyze it more today. Fair enough? Mm-hmm. Now, I want you to say something else too. The bells show up. The bells sit on top of mu, which is also perfect. And what did we notice about the plus or minus 2 standard deviations of the histograms you guys drew on the board versus the standard deviations, which you can't even see right here because the shadow is thrown on? The standard deviation of the population versus the standard deviation of the histograms you guys had on the board. Do you remember how they compared? You remember, Karen?
Yeah, it was half of what it was.
Yours were half of what your populations were. Good. I want to come back to that today too. That is really my favorite part. There's 3 things that are going on. One's the bell, one's the center, and one's the spread. And that half I want to come back to today. And it's not always half. For yours, it will always be half, but depending on other variables or one other variable, it can change. That's what I want to get into today. So what I want to do is I want to analyze. I want to shut this down for a sec. I want to fire up an Excel spreadsheet instead. What I've got here is an analysis of the blue dice. So which groups had the blue dice yesterday? 3 groups. We had 3 different groups with the blue dice. Awesome. I'm going to analyze the blue dice, and I'm going to do this without loss of generality. All I mean by that is we could have easily done this with the yellow dice, or the red ones, or the green ones, or the orange ones. The same argument's going to hold. It's just that the curves would switch to follow the average of those distributions. So if you buy it for blue, you'll buy it for any other ones too. And not just dice either. Any population that you know the distribution of. Fair enough? Cool. Okay. Now I put this here for reference. That was the average and standard deviation of the blue distribution. And you can't see this right now. I think I hit it up here. Is it up here somewhere? There they are, right there. That's the actual sample distribution, or excuse me, the population distribution of your outcomes. So what I did was I put the dice here and here, and then I made that little chart like you did yesterday with the 36 cells in it. And what I'm going to do is I'm going to randomly sample from those 36. And what you're going to see is, well, we're going to see right here. Here's a Monte Carlo probability distribution like you guys did yesterday. Make it fit a little bit better. That's a little bit better. Now, every time I press F9, I'm rolling dice again. Now, I'm rolling one heck of a lot of dice right now. I think I'm rolling 4,000. Let me see. Yeah, I've got 1,000 samples, each of which is rolling 5 times. So remember when you guys, I think you guys had to roll 100 times yesterday, right? I believe. Yeah. Because you had to roll 25 samples of size 4. Yeah. This is rolling 4,000. So basically, here's what you guys did yesterday right here. And it's just doing it that many more times. But this is why we invented computers, to do this kind of stuff. So every time I press F9, it's regenerating the distribution. Notice how it's changing a little bit each time? It's changing a little bit each time. Is that okay?
Yeah.
That has to be, doesn't it? Why? Why does that have to be okay? Think back to project number 3. When you compared your answers to the F9 part in Excel to your neighbors on project number 3, did you all get the same numbers?
No.
No, but what did you get the same values? The averages were the same, weren't they? You got 10 different values probably than your neighbor, but when you average those values together, they were arguably the same number. That's what's happening here. You're seeing the averaging out. Does this distribution shape look similar? Does that distribution shape right there look similar? Notice it's not changing very much. Does it look similar?
Yeah.
Heck yeah, it does. It looks like that. That's the static fixed distribution. This is the Monte Carlo approximation of it. Beautiful. This is how you do statistics in 2013. And more to come, more to come. All right, here's what you guys did yesterday. Now, this looks a little bit more bellish than yours did, doesn't it? Why?
You've got a larger population.
I've got 1,000 samples. I did 1,000 samples where you guys only did 25. So I've got a few more. I can There's 1,000 more. There's 1,000 more. There's 1,000 more. Now notice the bells are changing every single time, aren't they? But what's not changing? Yes, the average of that distribution is hovering where?
About 8.
Right. And oh, remind me again. Remind me again what mu was.
8.166.
Coincidence? Not at all. Glad I recorded that. Glad I recorded that for best in moment. Yes, you're hovering right on mu. Coincidence? No. If it was a coincidence, it wouldn't happen over and over and over again. That's the definition of an uncoincidence, if that's even a word. I don't know if it is. It is now. Now, did you notice I also shifted something? I changed the vertical axis from frequency to probability. That it became easier to look at because with 1,000 samples, those numbers were way too big. So all you're seeing now is roughly 14% of the time, you're getting your mode. 14% of the time. So I'm going to press it again. Roughly 14, roughly 14, roughly 14. Some of these bells are beautiful bells. Some of them are lumpy, but you're getting on average these beautiful bell shapes. These beautiful bell shapes. Just like on your take-home exam, when you press F9 and hold it down, thing just settles right into a nice bell shape. Now, let's do one better. Actually, let's do 5 better. I'm going to switch now, and instead of making you roll your dice 4 times and adding them and averaging them, we're going to roll 9 times. I didn't make you guys do this yesterday. But here's what it would look like if you did. How is that like the histograms that you guys were getting for your sampling distributions? How is it similar? Give me 2 ways it's similar. Give me 2 ways it's similar. Now, I heard one. Be brave, be brave.
The outliers are going away.
Oh, good. That's a 3rd way. I wasn't thinking of that. Darla said the outliers are going away. Hey, wait a minute. Hang on a second. Back up to 4. Notice we're still, oh look, there's one at 2.5 to 3 right there, right? Little rare bird. But every once in a while they pop in. Oh, there was a 2 to 2.5. Did you see that?
Yeah.
But now when we go to 9, those are pretty much essentially gone. Why are we losing even more outliers? Say that a little bit louder so I can hear it.
Because the sample group is getting bigger.
Why is that making the outliers go away?
They're too extreme.
Because they don't happen very often. So the chance of them happening 9 times in a row is got to be even less than happening 4 times in a row. X to the 9th power, Joe. To the 9th power versus the 4th power. So if the outliers are going away, wait, the area under the curve is still 1, right? So if the outliers are going away, where did their area go?
In the center.
Did you catch the distribution or the frequency chart up here, the probability charts up here? The high points before were at 14%. Now they're at 20%. Yeah? See? Little dance is doing up there. Back when the sample size was 4, the highest points were 14%. But now they're at 20%. Hover right around there. Cool? Does that make sense? So one way they're similar is the outliers are going away. What's another way they're similar?
Still bell-shaped.
They're still bell-shaped. That's a big one. They're still bell-shaped. And the 3rd way they're similar? The average is still hovering over the average. Good. Very good. The difference you guys already nailed. When the outliers went away, what happened to the curve? It's going like this and it's going like this. Good. Let's go out and do 16 die rolls. Let's do 16 die rolls. Uh-huh. You still got your bell shape. And that bell shape is still centered over. Oh, still good. Still centered over the average. We lost even more outliers, didn't we? Which means if we lost even more outliers, what else is happening? Gesundheit.
Your center's going up.
Your center's
You're
going
going
up.
up to
Look
25.
at the likelihood of getting towards the middle. 25% now, not 20 anymore. Let's go out to 25. 25. Now the high point's at 35%. Let's go out to 100. Thank God I didn't ask you to do this. It's ridiculous, right? It's ridiculous. 100. Each sample is 100 rolls that are then averaged. And it's doing that 1,000 times.
So,
Right? So 100,000 die rolls. This is why you invented computers. This is why we have them, to do this for us. I tried to go up to 10,000. And I finally discovered how to break Excel. I had a tab that was at 10,000. And you know how I'm pushing F9, it's going, oh yeah, I got this, oh yeah, I got this, oh yeah, I got this. With 10,000, I pressed F9, it was like,
vacuum.
and then like 5 minutes later, the graph changed. But it was great, because what did that graph look like with 10,000? That's what 100 looks like. What? Yes, it was one bar.
Over the average.
It was one bar that went to 100%. And that's the whole point. That's the whole point, is that those graphs just keep collapsing. These are called sampling distribution, the graphs of sampling distributions. They collapse and they get taller as your sample size goes up. Ask me that question, Kathy. Go ahead.
On your 100 rolls.
Yes, let's go back up. Oh, it's right here. Yeah.
I'm a little confused. Is that like taking 100 dice and rolling them all
It's
at
taking a pair of dice,
once? 2 dice.
rolling that 100 times.
100
So
times.
1, 2, and then
So we're still
averaging.
doing the total.
You're doing the same thing you did
Okay.
yesterday, but instead of 4, making you do 100
Okay,
times.
so the total of the 2 dice and then the total.
And then average those exactly.
Okay.
Now here's the catch. Here's the catch. This is cool, because as you have a larger and larger sample, the bar containing the average gets taller and taller and taller. Now that's good, because that means the likelihood of getting the average is going up. But you got to remember something. Let's go back to where you guys were yesterday. There's where you are, okay? How many of these, and there's 1,000 of them, when you run a research study, how many of those rows do you lay claim to? How many of those rows do you lay claim to when you run one research study? I just gave you the answer. You get one. You get one. You run a sample. So you have a population somewhere, and you draw a sample from that population. When you do a research study, you get one sample. So you might be this sample is size 20. This sample that's numbered 20, which means your average was 8.25. Which means, where is that in that histogram? Let's go find that particular one. Let's see, where would 8.25 be?
Right in the middle.
It'd be right here in the middle. So that's a pretty darn good sample, isn't it? That's a pretty darn good sample. But you could also be that 9.5 that's right there. And that 9.5 would be over, actually be in this bar over here, the way I've grouped them. Or you could also be that 6.75, which would be over here. And you might be that guy right there in that bar. You might also be that guy over there in that bar. Now, what's more likely? What's more likely? More likely is that you're going to be somewhere in here, but here's the kicker. There's a 14% chance that you're between 8 and 8.5. That means there's an 86% chance that you're too high or too low, isn't it?
Yeah.
You right? Does that make sense?
Yep.
There's a 14% chance you're in that bar. 86% of the time you're off of that bar somehow. But then you go, okay, but you're being too exacting, Sean. What if we said there's a 14 plus 4, let's call all these 14 if that's okay with you guys. Let's say there's a 42% chance that we're between 7 and 9. But there's still a 58% chance you're too high or too low. But then you go, oh, okay. Well, there's like a 95% chance. There's like a 95% chance I'm between 5.5 and 10.5. You see what I just did? I went out essentially 2 standard deviations, didn't I? Good. Hold that thought. Well, now, there's a 95% chance of that, but is that range too wide to be usable? Maybe. So what do you do to make the range not so wide? That's where the That's where you increase the sample size. You start increasing the sample size, because now, where's 95%? Basically here-ish, from like 6.5 to 9.5, right? And then suppose you think that's too wide, okay? Let's go to 16. Let's go to 25. Let's go to 100. Where's 95% of your sample now? Essentially between 7 and 9. So you went from what? 5 to 10 to 7 to 9. You still have the same percentage, 95%. But now your range is that much less. See what's going on here? Let's put the whole package together. Whole package together, which you're looking at right here. This is all 5 histograms at once down here on this bottom graph down here. It's a little hard to see for you guys in the back. I apologize. Here's the population parameters, which you do not know, right? You don't know them. You're doing the study to try to find out what they are. Here are the sample sizes, 4, 9, 16, 25, and 100. What I've got listed here are the averages of all 1,000 of those samples from the previous pages. I just pulled them into this sheet. And I've also got the standard deviations of those samples pulled into this sheet. Every time I press F9, Excel does a whole lot of work. Every time I press an F9, it's reshuffling those dice, throwing them, and re-averaging. What I want you to look at first is those histograms at the bottom. Are they looking roughly like they should look compared to what you guys just saw in the previous 5?
Yeah.
Pretty much, right? What's happening as the sample sizes go up? They're collapsing to the center. You're losing these outliers. These outliers that are a little bit present here are starting to fall off, and they're collapsing to the center. There's your 100 right there. Remember, the 10,000 one would have been great, but we lost that one. Okay, good. So those look exactly like they should look. Exactly like they should look. Fantastic, fantastic. Now what I want you to look at, I want you to look at the average averages. So, why am I saying average twice there? Why am I saying average twice? That might seem a little bit cryptic.
It was, data, you
Right?
rolled dice and
Then you average them.
and then you took other averages.
You got it. You guys got it together. What I have 1,000 samples, right? 1,000 samples. Each one of those samples has an average. And then what I did was I averaged all those averages. Does that make sense?
That's what you had us do.
Exactly.
We
That's
had
what I had
average
you guys
everything.
do. And you guys, your distribution was the graph of all those averages. All this is that entire histogram collapsed down to 1 point. The average of the histogram. So the average of the n equals 4 histogram is 8.12. The average of the 9 is 8.22. 60 is 8.14. 8.19. What do you notice about all those averages as I keep reshuffling all the dice?
Pretty
Staying
close.
the same.
It's staying the same, and it's also staying the same as what? They're all staying the same, and that number is also equal to what? You're looking in the right place, Karen.
The mu.
It's mu! Why is this good? You're not quite as excited as I am. That's okay.
Because it proves the point of the probability that everything's going to collapse to the center.
What are you interested in? What would you like to know more than anything when you run this research study?
That you're right.
Define accurate. Define, I love that, Ash. Define accurate, I love that. Yes, I like that. We've made a new drug that's going to lower LDL. What would we love to know?
Then it lowers LDL.
Right, that it actually does that. On average, that it actually lowers it. Are we ever going to know in the entire population of those taking it if it does? So are we ever going to know that? No. What's the best we can do? The sample. But the sample is basically the same thing as that. So are we happy?
Yeah.
Hell yeah, we are! Because we're getting that from a sample. Rather than sampling infinitely many people, we can sample a small number and get the same value. Yay us for doing less work and getting what we need to get. Now, do you remember the problem with that? Remember the problem? That's the average, correct? Do we always hit the average in our sample? No, that was the problem down here. It's a wide spread. That's why I want you to look at this number over here now, too. Okay? Now, this number here is essentially the value that the blue group got yesterday on the board. So you guys that had the blue dice, this is the numerical value of your standard deviation. We were doing it very, very ballparky yesterday with our fingers. I said, what is this? This is about 5, divide that by 4, it's about 1.25. Well, it's closer to 1.32 or 1.31 or 1.37. So we were darn close for government work, if you will. But what I want you to look at now is, how is that number related to the actual population standard deviation? Yes, it's less. But how much? We decided this yesterday.
Half.
It's about half. Good. About half, right? So I'm going to put 0.5 right there. Actually, I want to write it in words. 1/2. Excel was getting weird before. I was trying to type in fractions. It was converting into dates. Okay. Now, let's move away from you guys, what you did yesterday, and look into what Excel is doing today. How is that number right there, 0.86, related to that one? Now, it's not just 0.86. It's 0.89, 0.9, 0.89, 0.87, 0.88, 0.9. How is that number compared to that one? Ish.
About a third.
About a third?
Yeah.
I like that. 1/3. If I can spell it right.
1/3.
1/3. That's, what was that word you made up earlier, Karen?
Offline.
Offling. Good.
Offline.
Offling. Stood awesome. How's 0.64 0.71, 0.65, 0.66, 0.67.
Quarter.
Roughly a quarter? 1/4? I like that. Okay, good. How about 0.52? You could call it 0.5-ish, somewhere in there. What do you think? Roughly one. Like that knee, about 1/5, huh? Oops, don't get complacent. How about that one? Don't get complacent. Don't you dare say 1/6.
1/10.
If you were Europeans, this would be easier. It's about 1/10. Why do I say if you're Europeans it was easier? It would be easier?
Because you're on the
Because you're on the metric system in Europe, and all you're doing there is you're looking at that number and realizing it's 1 decimal off of that one. That's 0.26, that's 2.6. Right? Can anybody see me typing wrong while I'm trying to talk? There we go. Can anybody see a relationship
Yes,
into the predictability of these numbers
yes.
compared to these? What's the variable at work here? Let me see hands on this. This is the last, if you will, formula of the term. What's the variable at play here? Let me see hands on this. What is the variable at play? Braden, help me out. The sample size. Nee, how's it working? Go ahead, my friend. What were you going to say? Go ahead.
The sample size to the 2.
Nice. If you take, Michael, go ahead.
If you take the sample size, every time you double essentially the sample size, you're creating a different number on the other side.
Well, good. But we can get even more exacting than that. Nee is looking at the square root. The square root of the sample size. Did anybody wonder why I was using numbers like 4 and 9 and 16 and 25? It seems like weird things to go to. They're perfect squares. They're easy to square root. Now, you didn't know that when I did it, but I did it intentionally. Look at this. The square root of 4 is 2, 1/2, 1 over that. The square root of 9, 1/3. The square root of 16, 1/4. So what was I trying to do 10,000? Because the square root of 10,000 is 100.
Yeah.
And it would have been great, because then it would have been 0.026. A very nice number. Of course, it didn't work. Poor thing. So what you just saw is you just saw the third part. We're going to put all this together and synopsize here momentarily. Number 1, you get bell curves when you start sampling. Yay us. It's awesome. Number 2, those bell curves are centered on the average of the population. Yay us again. But as you sample more, the curves collapse inward towards that average. And predictably so. That's the cool part about this is they predictably collapse as a function of the sample size. They predictably collapse as a function of the sample. Let's put this all together. This is fantastic. This is the last couple slides of the term. Basically done. But I want to make sure you have all that in words. Write this down if you want to. It's posted online. I posted the PowerPoint to the schedule page on Tuesday. I'll post it again today, hopefully with this video if I have enough time to get in and actually edit it down and whatever I have to do, fuse the audio into it. Here's the goal. The goal is to do a study. And you're interested in knowing what the average and standard deviation of your population are. You want that. Like I said, write this if you need to, guys. It's posted for you. If you want to let it wash over you today, too, that's fine. It's totally fine. That's what you want. You don't know them, and you never will know them. But you want to know them. That's the whole problem. You want to know what they are. So, you do the best you can do. Go out and grab a random sample from it. I'm going to call it size n, just to make it general. Size n. As soon as you start sampling, something beautiful happens. You get a bell shape. Yay. That's wonderful. The bell shape almost immediately begins. Even with a sample of size 4, we saw that bell shape start to show up. That's fantastic. That's absolutely fantastic. So the bell, why are we happy about the bell shape? Why are we so happy about the bell shape?
Because
Michael, go. Oh, go, Karen, go ahead. No, please, me, go ahead, somebody. Go ahead, be brave. Because you get the symmetry. You get the utilization of all those wonderful percentages we've been talking. The 68, the 95, the 99, and all the rest. The 0.67 z-score is the first quartile. Excuse me, the negative 0.67 z-score is the first quartile. The positive 0.67 by knee symmetry is the third quartile. You get all those great stenormal, or quote-unquote stenosum, as Dustin was calling it, all those great little characteristics of the bell curve, you get to use then. Yay. This is even if your original distribution is ridiculous. Not even close to a bell. The bell kicks in. So instead of having to memorize a bunch of different distributions, you get to use one. I can tell again, you're not quite as excited as I am. That's okay. That's all right. This is a great thing. This is a great thing. Cool? All right, good. Also, the center of that bell, this is yay squared. The center of the bell is centered on the average. Now, I made up a symbol here. I hope you don't mind. I said the average of the sample averages. I called it X double bar. I hope that doesn't piss you off too badly. X bar is what you get in your sample. If you average all possible sample averages, it is equal to. That's not approximately. That's not ish. That's equals mu. I encourage you not to believe a word of what I just said about that. I proved it on the enrichment page of the website. I didn't believe it either. I'm like, there's no way. It's got to be ish. And then I sat down and did like, oh, I'll be damned. It's not ish. It's exactly. That's an equal sign. One of the few you see in this class. One of the few. If you're interested, check it out. It's pretty rad. Or you take a word for it. That's fine too. But the actual average of all the averages is mu. Holy crap.
That's awesome.
That is totally awesome. Totally awesome. The downside of it is, do you get all the sample averages in your research study?
No.
How many do you get?
One.
You get one, unfortunately. That's the problem. You get one. And that's kind of part two is, well, your X... Oh, crud.
Double X
Don't
bar
do
doesn't
it.
Right
equal
on
you.
the inside.
Single X bar... Single X bar doesn't actually equal mu. How does it compare? It's close to it on average. Good. It's close to it-ish on average, but it's not exactly equal to it like double X bar was. If I just put this over here. The tail end of this is going to be down here. That's good enough. I think we can get the idea. Yes? That's a problem. Because you have your sample average. You go, okay, I got my sample average. And this is the only data point I have besides its standard deviation. Your sample also has a standard deviation. We're getting to that in a second. That's the third part we have to talk about. So, I love the word ish. There's X bar. Remember, you don't know what mu is. You have no idea what mu is. But you want to know what mu is. So what are you going to do to that X bar? What are you going to do with the X bar? Why divided by 2? What are you thinking of? When you say divide by 2, Laura, you're not thinking of the X bar. You're thinking of you're thinking of the plus or minus.
Yes.
Now, here's the kick. Now, I love what Laura just said. She's saying divide by 2. That's for a sample size of 4. So technically, it'd be divide by root n for a sample size of n. See what I'm doing right there? I'm being a little more general. It might sound like I'm being a bastard. It's okay. It sounds like that. But when she said divide by 2, that's because we had a sample size of 4. Root 4 is 2. If we have a sample size of n, it'd be divide by root n. The problem with that is, what were we dividing by 2 yesterday? Do you remember what we were dividing by 2?
The standard deviation.
The standard deviation of the...
Average of the mean. Where? Of the average.
Which standard deviation were we dividing by 2?
The average of the averages.
No. Standard deviations.
Population.
The population standard deviation. Do we know what that is? Do we know No! That's the problem. We don't know what the population standard deviation is. So here we have these 2 wonderful question marks. We've got an X bar and we've got an S, and we have to say, crap, maybe. Or how close are these to their population values? Thank you, Lori, for illustrating the next point. What you have to do is you have to say, I've got a center and I've got a spread of my sample. How do I adjust those? Here we go. What you're going to do is you have to treat that S that you get that standard deviation. I'm going to call it a standard error because that's what it is called in inferential statistics and in every journal you're going to read. It's called a standard error. So on your take-home exam, there's a phrase on there I use. I call it standard error. Now you'll know what it is. Lisa, go ahead.
So that's dividing by the population.
It is. So what this is telling you, Lisa, is the standard deviation you get in that sample of size n is equal to that guy divided by root n. So in other words, you're going to know that from your sample. You're going to know how big your sample is. You can ballpark what sigma is from those 2 calculations. See, there's 3 variables. 1, 2, 3. You're going to have that one because you know how big your sample is. And you're going to have that because you know what your graph looks like. From those 2, you can extrapolate and find that. That's what I asked you to do, the last question of your take-home final. Does that make sense? Great question. Thank you.
In our calculator.
Yes, ma'am.
That our S.
Just S. It's just S, right? SX. That's all it is.
Okay.
Because now, this can get confusing because when is it S and when is it the standard error? That's a fantastic question, Lisa. I actually threw a stat of the day post up 3 months ago about this because somebody in 244 asked it. When is it S and when is it the standard error? And the question is it descriptive or is it inferential? And that's a great question because you may have forgotten what the phrase inferential versus descriptive statistics means. Let's take a trip down memory lane right now. What is the difference between descriptive statistics and inferential statistics? Who remembers? It's okay if you don't. It's been weeks since we've used this phrase. And 244 is all about inferential. We did a very little tiny bit of it in here at the beginning. What does inferential sound like? Inferring, you make predictions, Katie Powers. You make a prediction. You grab a sample, and you extrapolate out from that sample and predict what the whole population looks like. This is an inferential measure. So when your sample standard deviation, Kathy, like you just said, that S, when it is a measure of a sample that you're trying to extrapolate out, you treat it as a standard error. You treat it as a standard error. When all you do is you draw a sample and you're done with your sample, then you just call it S. It's simply a name difference. It's what you're treating it as. It's not an easy concept. It's not an easy concept, Lisa. I'm not saying you're going to understand this in 5 seconds. But when it's treated inferentially, it's the standard error. And when it's treated descriptively, it's just S. It's just S. There's no root N involved in it then. You'll make peace with it. You'll make peace. It's not something that's going to make sense immediately. I just wanted to answer your question. It's not that your question has an immediate answer. So that's the quick and easy answer that you have to make peace with. Fair? And that's all we're doing here is we're trying to approximate the value of the average, but we've got to put this plus or minus on it. So here's what we're trying to do, friends. This looks awful. Relax. It's nowhere near as bad as it looks. It is nowhere near as bad as it looks. No, you didn't. Just open your mouth a little bit. No, you didn't. I love that phrase, though. What do you want to know in this study? What would you want to know more than anything? But you can't ever know. You want to know what mu is, but you can't. So what do you get instead? You get your sample average and your sample standard deviation, right? So what you do is you hope, and this is the probability part, you hope that with a certain level of confidence that mu you're looking for is between 2 standard errors down from X bar and 2 standard errors up from X bar. Well, that sounds kind of kind of familiar, doesn't it?
Yeah.
What's 2 standard deviations up and down from average equal to? 95% of the occurrences. So when you guys hear the phrase 95% confidence in the media, that's what they're doing. They're creating a standard error from the sample. And all we do in 244 is figure out how to calculate those things. That's pretty much every day we do a new standard error measurement. You go up and down 2 of them from the average, and that's 95%. That's what I had you guys doing yesterday with your hands on the board. When you went like this, you said, where's 95%? Right about there? That's 2 standard errors. 1, 2. 1, 2, 95%. So now you've got 95% of the time, on average, you will have tracked the mu within those two ranges. Are you going to miss sometimes?
Yeah.
And we call those?
Outliers.
We call those the outliers. You can do a study where you're trying to find mu, and you can miss. This happens all the time. You'll very often hear of studies being overturned. Studies are overturned. If a study is done one time and never replicated, it's always suspect, because that one study could have been an outlier. When studies are replicated over and over again, we put a lot more faith in them, because what's the chance of them all being wrong? It goes back to what Lori said earlier. If it's an outlier the first time, it only has to happen 5% of the time or less. What's the chance of it happening twice in a row? 0.05 squared. 3 times in a row, 0.05 cubed. If you're seeing the same result, this is how I jokingly tell you guys, this is why I like when you work together. If you're all getting the same answer on an assessment, what's the chance you're all doing it wrong? Essentially 0. If you're all doing it independently and getting the same answer, there's a very good chance you're doing it right. Because the chance of you all getting it wrong puts you in the tail of the bell curve. You see what I'm getting at? That's the same thing here. If you're all getting it right, that means you're landing in here. On average. On average. I'm speaking in terms of averages, of course. Is that fair? So we're good out here? Yeah. Now, what happens to this? What happens to this? Here's where it becomes inferential, Lisa Bart. I have to re-answer your question. It was a great question, by the way. What happens to this as your sample size gets larger? That's the difference right there. It gets smaller as your sample size gets larger. So what happens to this range of values? It heads towards the middle. That's why the curves do. And that's the whole point. You want it to head towards the middle and increase in the middle because you have more and more of a chance of hitting close to where that average is. The average you can never see, but you're trapping in that interval. So what you're picking up is you're picking up precision as your samples get larger. You're picking up precision. Now that's a cool word. That's a cool word. And there's one that's related to it that you may have picked up in other classes. What word is often paired up with precision? Go ahead, be brave, be brave. Accuracy. Accuracy is often paired up with precision. I want to make sure we can tell the difference between accuracy and precision before we go any further discussing it. Okay? We are guaranteed one. We are not guaranteed both originally. Here are some targets that illustrate all the possible states of accuracy versus precision. Okay? There are 4 different states. You can have high accuracy, high precision, low accuracy, low precision. When I say high and low, I mean high means good accuracy, low means not good, poor precision. In these targets, if you want to make a correlation between what we're talking about and these targets, the bullseye would be mu. The bullseye is mu, and the dots you see, the shot pattern would be, each one of those would be a sample value that you're drawing. Okay, so one of these shows high accuracy, high precision. One shows low accuracy, low precision. One shows high accuracy, low precision, and the other shows low accuracy, high precision. Our job is to decide which one is which. Which one is which. And then we're going to tie it back into that great little interval you saw earlier. So no one wants to take a stab at one of those. Take a stab at these. Jamie?
Low.
This vote for low. Do we like low accuracy, low precision for this one? Jamie, explain.
It's not on mu, and it's really scattered.
Good. So what Jamie's doing is she's looking around at all the values, and she sees 2 scattered clumps and 2 tighter clumps. So the scattering of the clumps is tied to which, accuracy or precision?
The scattering is precision.
The scattering is precision. The tighter in they are, the more precise. Just like the tighter in your interval, the more precise. So if you want to tie this to a sample size, these would be smaller samples. These would be larger samples. If you're talking about as far as what happens as the sample sizes get larger. Very good, my friend, very good. So if these are both the low precision, one of them is accurate and one of them is not. Jamie says this is not accurate, this one is. I agree. If you're trying to hit mu, this is not accurate in hitting mu. This one is. This is centered on mu. That's centered on some other average that we're obviously either miscalibrated or in some other way missing. Does that make sense? Yep. So high accuracy, low precision, low both, low accuracy and low precision. So we got high precision over here. We got high precision here. What's this one?
Low accuracy.
Good, low accuracy. We're missing the target, but we're doing it well. Right? So this is one of those things, just adjust the scope. Adjust the scope. It's like that phrase, I'm lost, but I'm making good time. You're on. You're on. I think it's all of us. Do you ever notice that you get lost in the woods, you start walking faster? It's like it's gonna help you. Stop. Climb a tree. Look around. Anyway, you're missing the target. Here you're hitting the target, and it's clumped in. So if you think about sample sizes, large sample sizes, small sample sizes. Here's the good news from inferential statistics. 2 of those are never going to happen based on the central limit theorem. The only reason I put all 4 of these up is to make sure we know what accuracy and precision are. Why the top 2? Because we always get accuracy with the central limit theorem because the average of x bar is mu. So in other words, our gun is trained on mu. So we're not going to be trained off of mu. Very, very nice, Carrie. So we get this.